So what I've done is I've put together two types of dynamic studies that might be applicable to something such as a pallet here. And one is going to be, we have our normal force that's applied as an impulse. And so we're going to do 5,000 pounds distributed over the pallet, and we're going to apply that as an impulse in 10 milliseconds. And then the other type of dynamic study would be just a drop test. And we've really taken something that's pretty complicated, like a dynamic drop test, and essentially simplified it into how fast is this thing going, what's the angle that we're hitting at, or how high. So let's jump back over and take a look at these dynamic studies. And in this case, we're doing the drop test, and then we're also doing a nonlinear dynamic study. We also have linear dynamic solutions. And these are pretty much going to emulate what's happening on the shaker table. So if you do take your products and ship them out for physical testing, where they shake them, the harmonic analysis and or the random vibration are usually the types of frequency sweeps that people run dynamically. So that is an option in addition to the time impulse that we're going to look at. So it's a very similar process as before. We're going to start by looking at the impulse, and I can start a new study, and I go to nonlinear, and I can choose a dynamic study. And just like before, I can drag and drop my fixtures and my forces over to that new study. And that's already been done since we don't need to repeat. So now, if we edit the definition of our force, the force in the creep study, we ran a very long analysis, 7,200 seconds. And in this case, we're running a very short analysis, 60 milliseconds, with a 10 millisecond spike. And it's 5,000 pounds over distributed evenly over the top of the pallet with our same restraints that we had before. And then we just tell the study that we're going to run for a maximum of 60 milliseconds. And then we set our minimum time steps so that we don't miss anything. Now in this case, it's kind of interesting. So we'll animate. And now that we're dealing with simulations that are a function of time, post-processing or looking at our results becomes a little more interesting. So we're animating and we're trying to catch, what's going on here, but things are kind of going by a little too quickly. So this is where the ability to probe and manipulator plots are going to come in handy. So rather than just looking at the stresses at a single point in time, which I'm going to plot them very quick with a probe, I want to use an envelope plot so I can just see the worst case over all time steps simultaneously. And I can just go and say right-click, create a stress plot, and I want to do an envelope plot. So give me the worst case values across all time steps. And I would like some extra deformation so I can see what's going on here. So I can bump up my deformation scale to 20. And then let's cut a section. And then let's have the worst case stress location updated for us. So the response is a little different. So it's kind of interesting. The inertia, so rather than seeing the hot spots for the static load cases on the top of the pallet, we're seeing hot spots here on the bottom of the pallet due to the inertia and the bending of the material on the bottom here. So we're still at 22 megapascals, which is substantially under our yield strength limit for this material of about 100 megapascals, so we're still good to go. So setting up the dynamic study, similar feature manager, similar process as to what we use in linear statics. And in this case, this is a full nonlinear dynamic analysis, and I'm using a nonlinear material property with the complete stress strain curve. And we're still only looking at a solve time about 14 minutes in this case. So that's a fair amount of detail to be adding in a model that, 10 years ago, this would have been a half-day affair, but it was only a few minutes to set it up and solve it. So the second type of drop test, or second type of dynamic analysis that we're going to look at is drop test, which actually comes with Simulation Professional, and you will also get it if you have Simulation Premium. And this falls into the realm of explicit dynamics, which is the techniques that people use for car crash types of simulations. And we've taken this process and greatly simplified it. Let's get a quick animation going, and then we'll look at the drop test setups. So I've got the deformations blown up, I believe, by a factor of 5 here, just to make things a little more dramatic for your screen. And we have the max stress annotation following kind of where it's jumping around in the model as a function of time. And we're still doing okay. In this case, I actually ran with a really soft material, so we're not. The yield strength of this material, I used a polypropylene just for fun in this case. No, a low density polyethylene, be bad. And the yield strength, as we see on the legend here, is about 7 megapascals. And we're exceeding that, so we're definitely going to get some permanent deformation here in the corner. Now, in the case, let's say packaging for electronics or dropping a phone, we can also create time history plots of acceleration or displacement. So we might have a chip that can only handle accelerations up to a certain level, or we know that our hard drive can only handle a couple of Gs. So that's the type of simulation we want to do here, in addition to pallets. And the basic setup is pretty simple. We just tell SolidWorks how fast are we dropping it, or from what height do we want to drop this. And we pick a plane as our target. So I chose one here, or I built one on the corner so that we have a nice corner impact. And we turn on gravity, which is a law and also a good idea. And then we can add some contact damping and or a flexible target, depending on the type of floor that we're dropping our component on. So, but overall, we've taken the pretty complicated process of explicit dynamic analysis and simplified it down here into the drop test with this single drop test setup dialog. So I can take some questions here, and let me figure out how to get the mute off, and then we'll jump into elastomers and composites. But I do want to take a second here to get everybody unmuted. Okay. So you are all unmuted, and if you have any questions as of right now, we can cover those, and then we'll move on to the last legs of the presentation.
My only question coming in was just the nonlinear material library. Are the materials that are in SolidWorks, many of them have nonlinear properties already loaded? And where's the best place to get that information? Which you mentioned suppliers, but I didn't know if there was a database that we could tap into, even if it was a feed database.
Right. So actually, I've done a bit looking around. You know, there are commercial test labs that will give you data back in a format that you can pull into SolidWorks. You know, but that's on a per part,
sure,
or, per material basis. Surprisingly, there's no commercial, and maybe this is something I need to do. You know, what it is companies really find material properties as proprietary. You know, they spend money to do it, so it doesn't get out there. But in the SolidWorks libraries, anything that you see with an SS next to it has a stress strain curve.
Okay.
So right here, when we look at the carbon sheet steel with an SS, there's a stress strain curve already in the database. And then one place that I go to very often for polymers and plastics is I'm going to mute everybody real quick. I apologize. Hit me with the chat if there's further questions on this one. There we go. This is Campus, and you can search by supplier. So let's say BASF. We'll tell it, yes, we're accepting your terms and conditions. And then we can search through the different material types. And the nice thing about Campus over MatWeb is that we get XY data. So in this case, where I got my polypropylene glass fill properties was from a curve like this. So you can see that polymers are very temperature sensitive. So generally, you know, when I had a real job and I was doing this stuff for real, you know, I would choose the worst case curve for the worst case operating environment. And then we can get the XY data. Campus was nice enough to give that to us. And then we can punch this into the nonlinear curve inside SolidWorks. And then we can save it for reuse later. Okay. And any other questions for now? If so, send it off to the chat panel. I know there's a Q&A, but I don't have that up, so I'd appreciate it if we send your questions up to the chat panel. So we've done a drop test, an impulse load. We've done a creep analysis, and in addition to the initial linear static studies. And this is all based on one load case of our forklift being partially underneath the pallet. We would obviously also have a load case maybe where we're completely compressing the pallet, and that might be more realistic for the creep test. And then, is a stress strain curve the only nonlinear property I need? If you're doing linear elastic or linear plasticity, that should take care of it. In order to do the creep, we do need to get the creep constants. As I said, you know, one is an exponent on stresses, one is an exponent on time, and you know, a little bit of Google searching around, and you can start digging up those constants, and/or talk with material suppliers. And you'll see here for elastomers, that's a very good segue.